All right, in this video, we're going to continue our discussion of alpha carbon chemistry. This time, we're going to talk about Claisen condensations, which are somewhat similar to the aldol condensations that we learned in recent other videos. Okay, so we previously learned about aldol condensations that were reactions with aldehydes and ketones. Claisen condensations are similar reactions that involve esters. And so what's happening in this Claisen condensation is I take my ester and I react that with a strong base. What that's going to do is it's going to deprotonate my alpha carbon. That's going to turn it into a good nucleophile, and then that enolate is going to attack the carbonyl carbon of another one of the ester molecules. And the product of that is called a beta diketoester because the second diketo is in the beta position of to the ester. Now, a Claisen condensation is simply a nucleophilic acyl substitution reaction that we learned about last chapter involving carboxylic acid derivatives. In this case, the nucleophile is the enolate and the electrophile is the ester. So this is sort of a general schematic of the nucleophilic acyl substitution reactions, right? And in these reactions, the nucleophile attacks the carbon of the carbonyl group, and then the lone pair is going to go up on the oxygen. When we reform the carbonyl, it expels the leaving group. And so essentially we're replacing a leaving group with the nucleophile that's doing the attacking. And so what's going on in these Claisen condensation reactions is the enolate is my nucleophile, and it's attacking the ester. So this carbon is going to attack here. Ultimately, we're going to expel this alkoxide group, and this gives me my beta diketo ester, expelling the alkoxide of one of the esters as a leaving group. All right, so let's take a look at this mechanism in a little bit more detail. So the first thing we need to do in the mechanism is we need to make the enolate. So we have our strong base. It's going to deprotonate the alpha carbon of one of the ester molecules. Right, the enolate is now a good nucleophile, and so it's going to attack the carbonyl carbon of one of the other ester molecules, and then the lone pair, or the pi bond moves up as a lone pair on the oxygen. Then, like in other nucleophilic acyl substitution reactions, we reform the carbon-carbon double bond, and that expels the leaving group. Now, because we're in strongly basic conditions, this next step is unavoidable. So we still have that strong base floating around. This alpha position is now essentially doubly alpha. And so this hydrogen is particularly acidic because I form this ion, right? But I'm going to be able to draw resonance structures where I can move the lone pair to a double bond here and move it up on the oxygen and also up onto this oxygen. So it's doubly stabilized by being able to spread the negative charge onto these two oxygen atoms. And this last step actually drives this reaction to completion. And so it's unavoidable, and it's important for the equilibrium to favor the formation of the beta diketo ester. But because the formation of this ion is unavoidable in strongly basic conditions, we have that second step of the acid workup to give us our neutral product. Okay, there are a couple limitations to the Claisen condensation reactions. The first limitation is that the starting ester must have at least 2 alpha protons. It's the removal of the second proton by the alkoxide ion that's the driving force so that the equilibrium favors the condensation product. So this ester would be fine. It has 2 alpha hydrogens. This ester would not be okay because it only has a single alpha hydrogen. So this ester would be no good for a Claisen condensation reaction. The second limitation is the choice of the base, and actually we have to use a very specific base, and that the alkoxide ion must match the OR group on the ester. If we use hydroxide, then we're going to get a saponification reaction that we saw last chapter, and we're going to convert our ester into a carboxylic acid, and then in the basic conditions, we're going to have a carboxyl ion, and so it's not going to be able to undergo a Claisen condensation. If we use an alkoxide ion that doesn't match the OR group of our ester, then in a similar process, we're going to get trans esterification, and we're going to get a nasty mix of products. So if we have an ethyl group is our group on our ester, then we have to use an ethoxide ion. If we have a propyl group on our ester, then we need to use a propoxide ion. Or if we have a methyl group, we need to use a methoxide ion, and so on. Now we can do cross-Claisen condensations, just like we can do crossed aldol condensations, but many of the same limitations apply. So if one of the ester has no alpha protons, then the cross-Claisen condensation reactions will work okay. That will limit the number of products that we can get. Or we can do the Claisen condensation in a directed fashion, much in the same way that we did it with crossed aldol condensations. We use LDA as a base to irreversibly convert our ester into the ester enolate, and then we drop the other ester in drop by drop so that it reacts with the first ester and not with itself. And finally, we can also have intramolecular Claisen condensations, where I have an ester on two ends of a long enough chain of a molecule. We give this a special name. These are called Dieckmann cyclizations. And just like with aldol reactions, where we're forming cyclic products, the Dieckmann cyclization prefers formation of 5- and 6-membered rings. Alright, so I thought it would be helpful to look at some examples, but I didn't want to make this video too long, so I have a second video where we look at some specific examples of Claisen condensations.